Amateur astronomers using backyard telescopes are capturing images of 3I Atlas that are dramatically clearer than anything NASA has released to the public. These independent observers have documented 7 distinct jets stretching tens of thousands of kilometers into space, structured geometry, and features that NASA's billion-dollar instruments apparently cannot resolve. The discrepancy is not minor or debatable. It is stark, dramatic, and impossible to ignore. Chuck's Astrophotography posted a color-enhanced image that stopped researchers mid-scroll. The image showed clear central structure, bright forward emission, and layered coma, all captured with equipment you could fit in the trunk of a car. Meanwhile, NASA's Mars Reconnaissance Orbiter, equipped with the high-resolution Imaging Science Experiment camera, the same instrument that captures detailed Martian surface textures from hundreds of miles away, released a soft, washed-out blob barely showing the nucleus. This comparison matters because the Mars Reconnaissance Orbiter's HiRISE camera represents some of the most advanced imaging technology ever sent to space. This is the same camera that has photographed individual rocks, craters, and ice deposits on Mars with stunning clarity from orbit. Yet when pointed at 3I Atlas, it produced an image so lacking in detail that amateur astronomers using consumer-grade equipment comprehensively outperformed it. When Michael Jorger and Frank Nebling released their observations from Europe, they revealed something that fundamentally challenges our understanding of what NASA captured. Their images showed 7 distinct jets radiating from the nucleus. These were not chaotic plumes or random outgassing events. They were directional streams extending over 20,000 kilometers into space, maintaining their structure and orientation across multiple observations. The geometry of these jets defies simple explanation. Some jets pointed away from the Sun, which follows expected patterns from solar wind pressure, but others pointed toward the Sun, and one appeared to fire perpendicular to the Sun's direction entirely. This arrangement of jets suggests either an extremely unusual internal structure or processes we do not fully understand. Paul Craigs, another independent astronomer, has been releasing multi-night observations showing consistent structure across different viewing conditions. His commitment to precise calibration and comparison across multiple filters revealed aspects of the object's geometry that remain completely absent from official releases. The consistency of his observations, night after night, rules out atmospheric effects or processing artifacts. What he captured is real, repeatable, and dramatically more detailed than NASA's offerings. Ben Frederick's contributions add another layer to this story. Using a ZWO camera and telescope setup, equipment you can buy commercially without any special permissions or qualifications, he captured images showing distinct green outgassing. The color is significant because it indicates diatomic carbon, 2 carbon atoms bound together being released from the nucleus. This is not just a color preference or artistic choice. It is spectroscopic data revealing the chemical composition of the material streaming from 3I Atlas. But what stood out in Frederick's images was not just the color. It was the structure. Clear jets, defined coma, central brightness that suggested a compact stable core rather than a fragmenting rubble pile. These structural details matter because they tell us about the physical nature of the object. A fragmenting comet looks different from a stable one. The amateur images consistently show stability and organization that standard comet models struggle to explain. The timing and handling of NASA's data release raises serious questions about transparency and institutional decision-making. In late October, the agency held a press conference that had been hyped as the moment the public would finally see high-definition imagery of 3I Atlas. Scientists emphasized this would be one of the clearest views yet of an interstellar object. The anticipation was significant. This was supposed to be the moment when professional equipment would show us what amateurs could not capture. When the image appeared on screen, disappointment was immediate and widespread. The nucleus appeared as a few pixels. The coma lacked any meaningful definition. There was no visible detail on the jets that amateur astronomers had been documenting for weeks. No tail structure was discernible. No surface features could be resolved. Social media erupted within hours with side-by-side comparisons that were devastating for NASA's credibility. On one side, NASA's official release, a diffuse glow that could have been almost anything. On the other side, images from amateur astronomers showing layers of detail, structured jets, complex coma dynamics, and clear evidence of organized outgassing that NASA apparently could not or would not capture. One individual using a half-meter telescope from his backyard in Spain had produced images rivaling or surpassing what a multi-billion-dollar spacecraft delivered. NASA's explanation for the delay centered on the government shutdown that paused operations. Fair enough on the surface. Government shutdowns do affect workflows and can delay non-essential activities, but the timeline does not fully support this explanation. Nearly a month passed between when HiRISE captured the data and when NASA released the image to the public, and what they released required minimal processing. This was a simple image that could have been posted by a skeleton crew even during reduced operations. The prolonged silence and eventual disappointing release left many wondering if the delay was not about logistics, but about messaging, about deciding how to handle data that did not align with public expectations or amateur observations. While NASA maintained its silence, independent astronomers around the world kept working, kept observing, kept sharing their findings. They were not bound by institutional review processes or communication protocols. They simply pointed their telescopes at 3i Atlas and shared what they saw. And what they saw was extraordinary. The technical problems with 3i Atlas go far beyond simple imaging disputes. They touch on fundamental questions about how comets behave and what we should expect from interstellar objects. Avi Loeb, the Harvard physicist known for unconventional thinking about interstellar objects, analyzed the amateur images and identified multiple anomalies that challenge standard comet models. Loeb noted that the jets appeared too organized for natural outgassing. He calculated that producing jets this long and stable would require the object to shed approximately 13% of its estimated mass in a short period. Think about what that means. In order to produce the jets we observe, 3i Atlas would need to lose more than 1/10 of its total mass rapidly. That kind of mass loss rate is extreme and challenges our understanding of how comets survive close solar approaches. Natural sublimation, the process by which ice turns directly to gas when heated by the sun, typically produces chaotic, irregular venting. Picture a dirty snowball warming up. The outgassing happens wherever the heat penetrates first, creating random jets and plumes. But 3i Atlas shows stable directional jets maintaining structure across tens of thousands of kilometers. The organization and stability of these jets suggests something beyond simple ice sublimation. The rotation problem adds another layer of complexity that cannot be ignored. Earlier observations measured 3i Atlas rotating approximately every 16 hours, which is standard behavior for a comet of its size. But here is where physics creates a puzzle. If the object is tumbling at that rate while ejecting material in directed jets, those jets should appear smeared in long exposure images. The rotation would drag the outgassing across the sky, creating spiral patterns or diffuse clouds. Think of a lawn sprinkler spinning while spraying water. The water does not maintain straight lines. it creates arcs and spirals. The amateur images show exactly the opposite of what physics predicts. Tightly collimated jets maintaining straight lines and stable structure. No smearing, no spirals, no diffusion patterns that rotation should create. Loeb suggested two possible explanations, neither of which is satisfying from a conventional perspective. The first possibility is that the rotation has slowed dramatically since the early measurements. But this explanation has a fundamental problem. Asymmetric outgassing, which is what creates jets in the first place, typically speeds up rotation, not slows it down. When material jets from one side of an object, it acts like a thruster, spinning the object faster. For 3I Atlas to have slowed its rotation during active outgassing would require extremely unusual internal dynamics. The second possibility Loeb proposed is that the volatile ice deposits are located in extremely specific positions that only vent when facing the sun at precise angles. But this explanation strains credibility even further. Natural comets do not typically have ice pockets arranged in such precise geometry that they produce laser-straight jets stretching tens of thousands of kilometers. That is not how frozen rock and ice behaves after drifting through space for millions or billions of years. Random cosmic ray impacts, thermal cycling, and micrometeorite bombardment should have disrupted any such precise arrangements long ago. The brightness anomaly presents yet another challenge to conventional models. As 3I Atlas approached perihelion, its closest approach to the Sun, it brightened far beyond all predictions. This was not a slight deviation from models. It became roughly 4 times brighter than the most optimistic model suggested. 4 times brighter is not a rounding error or measurement uncertainty. It represents a fundamental misunderstanding of the object's properties or behavior. Researchers using data from SOHO, the Solar and Heliospheric Observatory, STEREO, and other solar observation satellites documented this brightness surge in detail. Multiple independent instruments confirmed the same result. 3I Atlas was releasing far more material and reflecting far more light than any model predicted. The color transformation adds another dimension to the mystery. The object went from dark red, consistent with a carbon-rich asteroid that had been exposed to cosmic rays for eons, to bright blue-green during its closest approach to the Sun. This color shift is not cosmetic. It indicates massive outgassing of diatomic carbon and possibly other volatile compounds. The blue color specifically requires extreme ionization, temperatures, and processes that typically destroy cometary material rather than preserve it. Yet despite these extreme conditions, despite the massive outgassing, despite the temperature and radiation environment near the Sun, 3I Atlas held together. It did not fragment during perihelion despite releasing enormous amounts of material at velocities high enough to overcome solar wind pressure. This survival is remarkable. Many comets fragment under far less stress. The fact that 3I Atlas maintained its structural integrity while undergoing such extreme outgassing challenges our understanding of cometary composition and cohesion. Standard sublimation models simply cannot account for this level of activity without the object having a surface area far larger than Hubble measurements indicated for the nucleus size. The math does not work. Either the nucleus is much larger than measured, which would require explaining why multiple observations got the size wrong, or the outgassing mechanism is fundamentally different from standard sublimation. When NASA finally held their long-awaited press conference, the scientific community expected detailed discussion of these anomalies. The directional jets demanded explanation. The brightness surge required analysis. The rotation problem needed addressing. The color shifts suggested chemical processes worth investigating. Instead, NASA offered what can only be described as a vanilla overview. The presentation included generic statements about interstellar objects. There was acknowledgement that 3i Atlas showed interesting behavior without specifying what made it interesting. No mention whatsoever of the 7 jets captured by amateur astronomers. No explanation for the 4-fold brightness increase that multiple solar observatories had documented. No discussion of why the object's chemistry appeared to shift so dramatically during perihelion. The presentation felt less like scientific disclosure and more like careful message management, acknowledging the object exists while systematically avoiding every detail that makes it genuinely anomalous. This pattern of limited disclosure has historical precedent that cannot be ignored. When Oumuamua passed through our solar system in 2017, official images were similarly vague. They were blurry, low resolution, lacking the detail that amateur renderings and simulations later provided. The pattern has led some researchers to suspect institutional hesitancy to share high-definition imagery of objects that do not fit conventional explanations. The technical capabilities make this pattern particularly troubling. NASA has instruments capable of capturing detailed surface features on Mars from orbit. HiRISE has photographed individual rocks no larger than a coffee table. It has resolved crater walls, ice deposits, and geological features with clarity that rivals aerial photography on Earth. The same instrument that achieves this remarkable resolution apparently cannot resolve clear structure on an interstellar visitor that amateur astronomers are imaging from the ground through Earth's atmosphere. Either the instrument underperformed dramatically, which is unlikely given its consistent track record before and after the 3i Atlas observations, or the data processing and release strategy involved decisions beyond pure technical capability. The latter possibility raises uncomfortable questions about what factors influence public data releases when observations challenge conventional understanding. Chuck's astrophotography enhanced live footage into color-graded images showing jets, coma layering, and central structure with clarity that stunned even professional researchers. These images were not random lucky shots or fortunate accidents. They represent the result of dedicated observers using extended exposures, advanced stacking techniques, where multiple images are combined to reduce noise and enhance signal, and careful processing to extract maximum detail from their data. The consistency across independent observers provides crucial validation. When multiple people using different equipment in different locations, under different atmospheric conditions, all capture the same structures, that represents replication. This is how observations become data. This is how anomalies become confirmed phenomena requiring explanation. And the data consistently shows features NASA has not acknowledged publicly. The democratization of astronomy through accessible technology has fundamentally changed the information landscape. For decades, space agencies held near complete authority over astronomical information. If NASA said something was a certain way, that was the authoritative answer. The public had no means to independently verify claims about distant objects. But modern equipment has changed this dynamic completely. Backyard astronomers can now capture data rivaling or exceeding what official sources provide. Digital cameras sensitive enough to detect faint celestial objects are commercially available. Computer software for processing astronomical images is freely distributed. Online platforms allowing instant global sharing mean information flows whether institutions want it to or not. The gatekeeper role that space agencies once held has been permanently disrupted. This shift creates inevitable tension. Institutions built on information control now face a public that can see for themselves. When official releases do not match independent observations, trust erodes. The erosion is not immediate or dramatic, but it is steady and cumulative. Each discrepancy adds to a growing skepticism about institutional transparency. Conversations happening in private research channels reveal the depth of frustration on both sides of this divide. Some NASA scientists privately acknowledge that the amateur images show details their official releases do not emphasize. They point to institutional review processes that can take weeks or months. They cite data validation requirements that demand multiple confirmations before public release. They reference communication protocols that require multiple levels of approval before images can be shared. Amateur astronomers counter these explanations with a simple observation. Raw data does not require months of review before sharing, especially when the observations are repeatable and independently verified. If multiple observers capture the same features night after night, the delay in official acknowledgement becomes harder to justify. The amateurs are not asking NASA to endorse their interpretations, just to share what their instruments captured. Avi Loeb has been more direct in his public statements. He stated clearly that NASA should be highlighting the anomalies, not downplaying them. The directional jets deserve rigorous investigation and open discussion. The brightness surge demands explanation. The rotation problems need to be addressed directly. Instead, the official messaging has been cautious to the point of evasion, acknowledging 3I Atlas exists while systematically avoiding the details that make it scientifically fascinating. Adding to the unusual nature of 3I Atlas is its sheer size. The object is described as being much more massive than expected based on previous interstellar visitors. Previous interstellar objects were 1,000,000 times less massive. This is not a small difference. 1,000,000 times more massive represents a fundamentally different class of object. This massive scale difference alone makes 3I Atlas genuinely unusual beyond just its behavioral anomalies. The story of 3I Atlas does not exist in isolation. Other comets are displaying their own unusual characteristics during this same observational period. See 2025 R2 Swan, another recently active comet, has developed an anti-tail, material pointing toward the Sun rather than away from it. Anti-tails are not unheard of in cometary science. They occur when large dust particles spread along a comet's orbit, and Earth's viewing angle makes them appear to point sunward. But they remain unusual features that require specific conditions to manifest. Seeing two comets develop anti-tails during the same observational window raises questions. Is this coincidence, or is something about current solar conditions triggering behavior we do not fully understand? These are hypotheses, not confirmed explanations. The data clearly shows the unusual features, but the mechanisms driving them remain unclear and demand investigation.